Hello everyone and welcome to our next lesson. In this video, we will review the concepts of the first law of thermodynamics, heat and work, and the general energy balance equation. All of this are in preparation for the problem-solving part of our lecture, which will follow later. Let's begin with a quote from Albert Einstein. Classical thermodynamics is the only physical theory of universal contents which I am convinced will never be overthrown. This is a testament to the universality and reliability of the laws of thermodynamics in describing energy relationships of systems. Throughout our lessons, we will be exploring energy relationships that define a large aspect of our current way of living. The statement of the first law of thermodynamics is based on the conservation of energy. Simply stated, energy can neither be created nor destroyed. It can only be transferred or transformed. For an isolated system, that means that the initial and final energies are equal. The total energy of a system can be described in three terms: internal energy, kinetic energy, and potential energy. The internal energy is the inherently contained energy within the system. The kinetic energy is the energy possessed by a moving body. The potential energy pertains to the energy stored by a body that is acted upon by the pull of gravity. For closed and open systems, energy can be exchanged with the surroundings in the form of heat and work. Shown here are examples of how energy is transferred to and from a closed system. In this figure to your left, a stirrer transfers shaft work into an enclosed gas. We say that work is being done to the system. This work done on the closed system will result to an increase in the total energy, manifested by an increase in temperature. In this figure to your right, we have a closed system releasing heat into the surroundings. The release of heat results to a decrease in the total energy, manifesting with a decrease in the temperature of the gas. Both heat and work are important parameters in thermodynamics and expect that we will encounter them continuously. We then say that the total energy change of a closed or open system is equal to the amount of heat and work transferred either to or from the system. We now have the mathematical statement of the first law of thermodynamics. The total change in energy is equal to the heat plus the work transferred. It is important to note that heat and work are not static. They are transferred properties. That could be heat transferred or work done, and it would be better if we always say and view it that way rather than just saying heat and work. Expanding our total energy term, we now have the change in internal energy plus the change in kinetic energy plus the change in potential energy equal to the amount of heat and work transferred. Here we also have the definitions of kinetic and potential energy. We will go back to this equation later, but for now, let's focus on heat and work. Both heat and work are forms of energy that are exchangeable through the system's boundary. If we consider this our system and our surroundings, we then say that heat entering the system from the surroundings is positive and heat leaving the system is negative. On the same note, work being done to the system is positive, while work being done by the system is negative. Remember that all of those are sign conventions and are provided for the purpose of mapping the direction of flows of the energies. In some cases, the sign convention for work is the opposite of what we have presented here, so please be vigilant on your signs of heat and work. The important thing is you understand the meaning of these symbols. Another important thing to note is that the amount of heat transferred is different from the rate of heat transfer. That's the same for work. The amount of work done by the system or surroundings is different from the rate of work done. The rate of work is referred to as power. Take note of the differences in representation. The absolute amount of heat and work are represented by capital Q and W respectively, while the rate of heat transfer and the rate of work done are represented by the same letters, but they have a little dots on the top. This lets us distinguish between the two different quantities. The amount of heat and work transferred are measures of energy, while the rate of heat and work transfer are measures of power. Presented in this table here are the different units that we may encounter for both amount and rate of heat and work transfer. For the amount of heat or work, we use joules or Newton meter under the SI system. We use foot-pound force under the American engineering system, and we use BTU or British thermal units under the British imperial system. For the rate of heat or work transfer, under the SI system, we use watts or joules per second. For the American engineering system, we have foot-pound force per second. And under the British imperial system, you can either use BTU per hour or horsepower. Take note that BTU per hour is not equivalent to horsepower. We will encounter mostly SI units, but you still need to be familiar with the other units as well for the purpose of conversion. For heat transfer, we can estimate its value from the general heat transfer equation. Q is equal to UA delta T. Q dot is the rate of heat transfer. U is the overall heat transfer coefficient. This should not be confused with internal energy. A is the heat transfer area, and delta T is the driving force or the temperature difference for the heat transfer. For now, you don't have to worry about using this equation, as this will be tackled more in your future courses. For now, we want to determine the amount of heat transferred using these equations. These are commonly used in calorimetry. We have Q is equal to N Cp delta T for constant pressure systems, and Q is equal to N Cv delta T for constant volume systems. For the amount of work performed, we will discuss here the two major types encountered: expansion work and shaft work. The other types of work will be explained as we encounter them in other lessons. Expansion work can be determined by the negative integral of pressure times the differential change in volume. The negative sign provided here is just for our sign convention. This means that if the system expands, it performs work on the surroundings, therefore the work is negative. If the surroundings exert a constant pressure, such as our atmosphere, we can simplify the solution to just negative of the external pressure multiplied to the volume difference of the system, that is final volume minus initial volume. For this definition, we can generalize that no expansion work is done if there is no change in volume, because for constant volume systems, V2 minus V1 is equal to 0, therefore expansion work is equal to 0 as well. This is the case for systems with rigid boundaries which do not allow for expansion. Also, no expansion work is done if the external pressure is 0. That would be if the expansion is done against a vacuum. Another commonly encountered work is shaft work. This is present in steering, in turbines, and in compressors and other thermodynamic devices with rotating parts. This is determined as the negative integral of the torque applied to the shaft multiplied by the differential change in the angular position. Finally, we arrive at the general energy equation. This is the equation that we will use for all types of systems, be it open or closed, steady or unsteady state. We write it as the rate of change of the internal energy in the control volume plus the net change in the total energy of the system as introduced by the flow streams, equal to the rate of heat transfer plus the rate of power transmission or the rate of work transfer. This single equation is the backbone of our energy analysis for any system we encounter. For open systems, this can be used in conjunction with the material balance to completely describe the mass and energy relations in the system. For the purposes of calculation and problem solving, let us present the simplifying cases to this energy balance. If the process is at steady state, meaning that the properties of the system are not changing with respect to time, we can cancel the first term. That is a time derivative, and all time derivatives of properties are 0 under steady state conditions. Next, if we assume that the system is adiabatic, there is no heat transfer. Therefore, the rate of heat transfer is 0. Next, if we assume that the walls of the system are rigid and allows no room for expansion, expansion work is 0, and the change in internal energy in the left-hand side of the equation will be changed to enthalpy. That came from the definition of enthalpy, which is internal energy plus PV. If there's no expansion, delta PV is 0, making delta H equal to delta U. Also, for non-flow systems or constant velocity systems, we can remove the kinetic energy term. For a stationary system with no appreciable height difference between inputs and outputs, we can remove the contribution of the potential energy. These are the common assumptions that we can use to simplify our energy balance. Keep in mind that not all of the terms will be used for your solution in any problem. That's why it is important to know the scenarios for simplification. With the end of this lesson, let's take a look at some important takeaways. First, energy is always conserved. Second, internal, kinetic, and potential energies are the contributors to the total energy of a system. Next, heat and work are not static, they are transferring quantities. Next, it is important to represent heat and work transfer with the proper sign to indicate the direction of transfer. Next, simplifying assumptions can be applied to the general energy balance to make it manageable. Following this lesson, we will have separate videos for the discussion of solutions for the first law analysis of some systems. That's the end of this lesson. I hope you have learned something. Thank you for listening, and as always, keep safe.